Pretty good. So let's see, last time I was showing you a method to compute the Poincar series of a Coxeter group inductively, recursively. So we said that we have this formula that if you add up over all the parabolic subgroups, minus 1 to the number of generators divided by the Poincar series of the parabolic, then you either get 0 if W is infinite, or you get Q to the length of W naught divided by W of Q if W is finite. Okay. And we saw in an example last time how this formula reduces the computation of the Poincar series of W to the computation of the Poincar series for all of its parabolic subgroups, which are smaller. So then we can do this inductively. So the first thing I would like to do today is prove this theorem for you. So what I'm going to do is multiply by W of Q and the nice thing is that we know what this quotient is, right? This is just the Poincar series for the parabolic quotient. And that makes it less mysterious why we're getting fractions here. Okay. So what's this? This is summation over subsets of S. Now, if you remember what this is basically well, I'm not doing anything here. I'm just saying that the definition of W super J is the generating function for the lengths of the words in W super J. And what I want to do now is switch the order of summation. Okay? So instead of first summing over J and then summing over the W's in that parabolic quotient, what I'm going to do is first sum over all the elements of my Coxeter group, and then sum over the J's such that that parabolic quotient contains that little W. Okay, so all I did is switch the order of summations. And then do this. Okay. Now, what I want you to notice is that over here, this thing doesn't depend on J. It only depends on W, and so I want to factor it. So I get Q to the length of W times summation over the J such that the parabolic quotient contains W of minus 1 to the J. Okay. So I get this. And what I would like to do is compute this summation right here. So for each fixed W, have to do is compute minus 1 to the size of j over all the j such that the parabolic quotient contains w. Now let's remind ourselves what this means. What this means is basically w is in w super j if there are no reduced expressions for w that end in a letter in j. Okay? So what am I saying here? Well, wj contains w if and only if no reduced word for w ends in j, in some letter of j. Okay? So basically, what I can do is look at all the possible last letters that w can end in, and j can't contain any of them. Yeah? So j intersect, let me call it, I don't know, S of w is the empty set where S of w is the possible last letters in a reduced expression for w. Okay? So which j's am I summing up over here? Basically, the j's which are disjoint with S of w, and that means basically the j's that are contained in the complement of S of w. S of w. S of w complement. Okay. And I don't know if you're familiar with this expression, but if you look at this carefully, you're going to see that this is exactly 0 in most cases. Okay, because let me just do this very quickly. So if you do this for some set A, then what are you going to get? Well, basically, you're adding up over all subsets of A. So how many times are you going to see minus 1 to the k? Well, basically, the question is how many k subsets do you have here? So this is size of A, choose k, and you're summing up over all values of k. And this, by the binomial formula, by the binomial theorem, is 1 plus minus 1 to the size of A. Okay? And that means that this is basically 0 unless A is empty. So if A is not empty, then you get 0. What about if A is empty? If A is empty, then we're adding over the subsets of the empty set. The empty set only has one subset, which is the empty set. And we add minus 1 to the size of it, so that's 1. So what I have here, what I have in this parenthesis, is probably 0. It's 1 in exceptional cases. So this is 0 unless basically S of w complement is empty, which means S of w is everything. Okay. Well, let me. Okay. Now, what does it mean for S of w to be everything? It means that every generator can be the last letter in a reduced expression for w. Okay. But remember that when can a generator be the last letter in a word for w? when multiplying by that generator makes you shorter. Okay? So S is in S of W if and only if some reduced word for W ends in S. And we said last time that this is equivalent to saying that when you multiply by S, you make W shorter. Okay? So what am I saying if S of W is equal to S? I'm saying that every S has this property. Every S makes W shorter. And by the homework, you know what that means. That means that W has to be the longest word. Okay? So S of W is equal to S if and only if W is the longest word. Now, if there is such a thing as the longest word, that means that already the group is finite. Okay? So what am I saying here? If W is infinite, then there is no such thing as the longest word, and that means that all of these guys are 0, and that means that the sum is 0. Now, if W is finite, then all of these terms are 0 except for one of them, which is the one for the longest word. And for the longest word, I have a 1 here times q to the length of W naught, which is exactly what I need. So that means that by this reason, basically, this equals what I want. Any questions about that? Okay. So this fairly short computation gives me a very powerful technique to compute these Poincar series. And I pointed out to you last time, basically this allows you to do it for any for almost any reasonable Coxeter group. You can basically do this and recurse. And then compute W of Q for any W. So this is the proof that I owed you last time. And this is all that I want to say for now about the Poincar series of a Coxeter group. Now you will have more to say about this in the homework. Okay. So now I would like to switch topics. We're going to continue talking about enumeration, but in a slightly different way. So what we're going to talk about now is Mobius functions. Okay. So, well, let me say, yeah, sure. So what does this mean? Well, each poset has something called a Mobius function. And what this is that for every pair of elements, x smaller than y, smaller than or equal to y, you get a number. Okay? The number is called mu of x comma y. And this number is defined recursively. Okay? So what's the initial case? Well, basically, y has to be bigger than x, bigger than or equal to x. So the smallest that y could be is x. If y is x, if these two guys are equal, then the Mobius number is 1. Okay. So 1 if y is equal to x. And if y is not equal to x, then it's bigger than x. And what you're going to do is look at everything between x and y and add up all the things underneath in the following way. So you look at all the things between x and y and add up all the Mobius numbers mu of x comma z and make a negative sign. So you see I'm adding up for all z's between x and y, except that I'm not including y in here, because this is supposed to be a formula for mu of x comma y. And so I don't want a self-referential formula. Okay. So let me show you how you do this in practice. I mean, this is a lot more concrete than it might seem from this definition. So let's do it for an example. So our favorite poset is this one, the Bruhat order of S3. At least that's our favorite poset so far that we have seen the most. So for each pair of numbers that one is smaller than the other one, I'm supposed to give you a number. Okay. Now, let me just show you the numbers mu of bottom element, comma, y. Okay. So we're going to compute mu of bottom element, comma, something bigger than it. So you do it recursively. Okay. You start by saying, okay, what's mu of bottom element, comma, bottom element? Was 1. Okay. And then you start working your way up the poset. And you say, okay, what number should I put here? Well, basically what I'm going to do is look at everything that is smaller than this guy, add up those numbers, and change the sign. So I look at everything underneath, I see a 1, and I change the sign. So I get a negative 1 here, and the same thing here. Now I go here. So what number should I put here? Well, I look at all the things that are smaller than this one. -1, -1, and 1. They add up to negative 1, and I switch the sign. Here, the things that are lower are the same ones, so I get a 1 also. And what number should I put here? Well, I have to add up everything that is smaller than this guy. So 1, 1, -1, -1, 1. So I get 1, switch the sign, and I get negative 1. Okay? So these 6 numbers that I'm writing here are mu of bottom element, comma, all the different elements. Now to compute the whole Mobius function, you have to do this for each bottom element. So for example, how do you compute mu of this bottom element, comma, everything in between? Well, you basically do the same procedure, except that you only look at the things that are higher than it. And you get a different set of numbers and so on. Now generally, this Mobius function is a function of 2 parameters, but we often care about these the most. Mu of bottom element, comma, something. And this is how you compute them, just recursively. You look at everything below, add it up, switch the sign. Okay? So let's do a more complicated example. A more interesting example, let's call it that way. I like that better. So here's what I want to consider is the poset of faces of a cube. Poset of faces of a cube. Okay. So here's my cube. And it has many faces. It has 2-dimensional faces, 1-dimensional faces, zero-dimensional faces, which are the vertices. The empty set is considered a face, and so on. So let's draw this poset to some extent. So what's the largest face of the cube? Well, the largest face of the cube is the cube itself. Okay. The only three-dimensional face that I have. Now, what are the two-dimensional faces? Well, basically, they're the six faces of the cube, right? So then I have 1, 2, 3, 4, 5, and 6. So this is dimension 3. This is dimension 2. How many one-dimensional faces do I have? Well, basically the number of edges that I have. So if you count them, there's 4, 8, 12 edges. Okay. So how many zero-dimensional faces do I have? Well, the 8 vertices, right? So I get this. And then, by convention, we like to put a bottom face here, which is the empty face. And the reason for that is basically that we tend to like posets with a bottom and a top element. They behave nicer, and really there's not too much of a difference there. Okay. So this is kind of what the poset looks like, except, of course, there's a lot missing here because we have to basically keep track of which point is contained in which segment is contained in which phase, etc. And it would take me the whole class to do that, so I won't. But for example, we know that this guy covers all of these, etc. But I claim that we can compute these numbers without having to draw the whole poset. So let's go ahead and compute them. So again, let me compute the Mobius numbers 0, something. Okay. So that means I'm going to put a number on each element of the poset. Now for the bottom guy, you always put a 1, right? Now, what should I put for these? Well, all of these contain a unique guy, which is the empty set. And so for each one of these guys, I should put a -1. So, right? So -1, -1, -1. Okay. Now, what about one of these guys? So these guys, make sure you remember. So this is the empty set. These are the vertices. These are the edges. These are the two-dimensional faces. And this is the whole cube. Okay. So for an edge, what is the Mobius number? Well, basically, I have to see what is below. Now, you have to be careful because, remember, below doesn't mean a lower height. It means less than in the poset. Okay. So, for example, what is less than this edge in the poset? Well, I don't know which edge it is, so I can't tell you exactly which two vertices, but there are two vertices. Yeah, I know that. 1, 2, and then bigger than this one. Okay. So no matter which guy I have here, I'm going to have -1 plus -1 plus 1, which is -1. I switch the sign, and I get 1. Okay. And so all of these are 1s. 1, 1, 1, 1. What about a two-dimensional face? This one. Well, again, I don't know which face it is, so I can't tell you exactly which edges it contains, but I know how many it contains, right? Each face is a square, and so it contains exactly 4. So I don't know which ones, but let's say it's this one, this one, this one, and this one. Okay? How many vertices are you going to find? Well, 4, because no matter which square this is, there's going to be 4 vertices. So, and these two are going to be 2 of them, right? And 2 more. So, I don't know, something like this. And in the end, it's going to look something like this. There's too many, right? But what do I know? I know that there's exactly 4 guys at this level, 4 guys at this level, 1 at this level. So I know what the numbers are. 4 minus 4 plus 1 is 1. Switch the sign, -1. Hopefully you see a pattern emerging here. Okay. What about for the top guy? Well, the top guy contains everything. Okay. So, I don't know, is our pattern going to break here? Let's see. You add up 6 two faces minus 6 plus 12 edges plus 6 minus 8 minus 2 plus 1 minus 1. So we get a 1. So you might start getting a little surprised here, and you might wonder, okay, why am I defining this if it's just minus 1 or 1 according to the height? Well, you can imagine that so far we only have minus 1s and 1s because these are very special posets. If you do this for some random poset, you get bigger numbers, smaller numbers, zeros. But these are very nice posets, and that's why we get -1s and 1s. Let me point out something to you. Let me show you why, no matter what polytope we started with here, we should expect only 1s and -1s. So this is not an accident, and it's not about being a Q, it's about being a polytope. And you know that you can prove that already. Let's do it for 3 polytopes. So why should I have expected to get like this Mobius function no matter what 3 polytope I get? Because no matter what 3 polytope I get, here's the 3-dimensional, 2-dimensional, 1-dimensional, 0-dimensional, and the empty set is called -1-dimensional. Okay? So I don't know. The poset looks like something like this. Okay? So let me do this again, but without referring to the cube. Let's say that this is just some 3-dimensional polytope. It doesn't matter which one. Here, of course, we get all 1s because there's only one guy. It's a 1. Here, of course, we get only -1s. Right? Because they only are on top of this guy. Now here, these guys are edges of my polytope. So no matter what polytope it is, an edge has 2 vertices. So below something like this, I'm going to have 2 -1s and 1 1. And so that means I have to have all 1s here. Okay. Now, a 2-dimensional face, that's a polygon. I don't know what polygon it is. That polygon is a k-gon, let's say. Well, if it's a k-gon, that means it has k edges and k vertices. And so the k and the -k are going to cancel out. I get a +1 and -1s here. So far we're getting this very easily. Here we're going to have to work a little bit more. What am I going to get here? Well, I have to add up all of this stuff. So here I get minus number of faces. Here I get plus number of edges. Here I get minus number of vertices. Here I get +1. And so the number that I'm supposed to put here is the negative of this stuff. V minus E plus F minus 1. And at this point, you either have seen this before or you haven't seen it. Every polytope has V minus E plus F equals 2. 2 minus 1 is 1. Okay. So you start seeing that actually this Mobius function is a very nice function, and there's a lot that comes into play. So this right here is called Euler's formula for polytopes. And you might know that actually Euler's formula holds in any dimension, not just in 3 dimensions. And because Euler's formula holds in any dimension, that means that no matter what polytope I put here, I get 1s and -1s. Okay. So let me just tell you a little bit of kind of hand waving about how you're supposed to think about this Mobius function. Well, the Mobius function you should think of the reason that this works is basically because of the following. You may or may not have seen topology. In topology, basically, you want to understand when two spaces are equal or different from each other. So you probably have heard of whether a ball and a, or what is it? I guess they always talk about the donut and the coffee cup. And they are the same because they have the same hole, and you can kind of morph one into the other one. But for example, you cannot take a donut and make it into a ball. And the way that you prove something like this is by assigning to each topological space an invariant called the Euler characteristic. And you prove that if you move a space around, you're not going to change the Euler characteristic. And then you prove that the donut has one Euler characteristic and the ball has a different one. One way of understanding this is basically saying this is the Euler characteristic of a polytope. And a polytope is a ball, and it has the same Euler characteristic, and you can think of this as a topological fact. This is very hand-wavy in case you haven't seen this stuff. But the Mobius function, you should think of it in a similar way. The Mobius function is kind of a topological number that you associate to a poset. So is the Euler characteristic so the Mobius number mu of x comma y in quotations is the Euler characteristic of the interval x comma y. Okay. Now I'm putting this in quotations only because I'm not saying exactly in which sense it is, but this is really a pretty precise statement. I mean, this is not just hand waving. There is a sense in which this is very precise, and if you know some topology, come talk to me and I'll tell you about it. And one reason that people like to study the Mobius function is that it generalizes a lot of the things, a lot of very nice things in the literature. For example, we see how Euler's formula very naturally comes into play here. You may have heard of the Mobius function as something in number theory and not something in combinatorics. Yeah? So there's something called the Mobius number, the Mobius function that associates to an integer a number. And this is a special case of this. And so this generalizes the Mobius function of number theory. And it generalizes the inclusion-exclusion formula of combinatorics. So all of these things are part of the same story, which is the story of Mobius functions in posets and Mobius inversion. Okay? And these are just some good reasons why whenever a combinatorialist sees a poset, one of the first things that they're going to ask is, what is the Mobius function? The Mobius function really tells us a lot. So the next thing that I would like to claim is that what I did there is not an accident, and that just as phase posets of polytopes have a very nice Mobius function, so do Coxeter groups. Okay. So, what I'm going to show is basically that the Mobius function is just ones and negative ones in this way, which maybe doesn't look surprising to you because the two examples that I have there have that property, but this is a very rare property, and a very interesting property and a very useful property. So, proposition. Let's say that you have a graded poset. Okay. Then the following are equivalent. 1, the Mobius function is that simple. The Mobius number of x comma y is just plus or minus 1, and the sign is just determined by the number of levels separating x and y. Okay. first thing. And the second thing is that in any interval x comma y, there is an equal number of elements of even rank and elements of odd rank. Now you did your homework already, right? So in your homework you already proved that Coxeter groups have this property. And that means that you proved already, well, that as soon as I'm done with this proof, we will have proved that the Mobius function is what I claim that it is. Okay. And I should tell you that, as you can imagine, this is a very nice family of posets. We like posets that have this property. We like them enough to give them a name. And because of that, we call them Eulerian posets. So a poset is Eulerian if it has these two properties which are equivalent to each other. Okay?
Excuse me.
Yep.
I can't read the two. In any interval x, y, there is...
In any interval x comma y, there is an equal number of elements of even rank and elements of odd rank. Okay. Proof. Let's show that 2 implies 1, which is basically the main, well, we're interested in that because by proving 2, which you will do in your homework, we will get 1, which is what I'm claiming. Okay. Well, how do you prove something like this? Well, basically, these things are defined recursively, and so it's very natural to try to prove this inductively, because this number is defined in terms of smaller ones. So let's induct on the difference in ranks between x and y. Of course, the first case is trivial because if the difference in ranks is 0, then if x and y aren't at the same level and one of... Now, this is, of course, for x less than or equal to y, right? Because that's the only place where the Mobius function is defined. So if they have the same rank, they must be the same element. And then we know that mu of x comma x is -1 to the 0. Okay. Which is good. For the initial case, we use the initial case. And now we induct. So now suppose true for rank of z less than rank of y. And let's prove it for y. Okay. So let me show something to you, which maybe you noticed already, which is that the way that I define the Mobius numbers by saying that mu of x comma y is minus the sum of the other ones. Basically, what I want to accomplish is that if I add up the numbers between x and y, I always get 0, because the top one is minus the other ones. Okay? And so let me rewrite that condition in this way. 0 is equal to the sum of all the numbers in the interval, where now I include y. Okay? Now, I know what all of these numbers are, except for mu of x comma y, right? So I know that all of them are -1 to the, actually this is x comma z, I'm sorry, right? So I know that all of them are equal to this, except for x comma y, right? So let me correct for that by subtracting mu of x comma y and adding minus 1 to the rank of y minus rank of x. Okay. And of course, what I would like to prove is that actually there is no correction term here, that this really is 0, and this is really an equality. Okay. Well, look at this. How many plus 1s and how many minus 1s do I have here? Well, this is the interval between x and y. And I know that this interval has the same number of elements of even rank and of odd rank. And the ones of even rank contribute one sign, and the ones of odd rank contribute the other sign. So because here there's an equal number of even and odd elements, that means that I have an equal number of plus 1s and negative 1s. Equal number of 1s and negative 1s. And that means that this sum is 0. Here, I'm using that my interval xy has this property, which is what I'm assuming. That means that this is 0 minus mu of xy plus minus 1 to the rank of y minus rank of x. And that does it. It does it because that proves that mu of xy is what I want it to be. So there's not too much to say there. The reverse direction is almost exactly the same. So you should do it, but you'll see that you're going to make exactly the same argument. So that means that we have two different criteria for Eulerian posets. Okay? And so let's talk about some examples of Eulerian posets. So perhaps the simplest example of an Eulerian poset is one of our favorite posets, which is the poset of subsets of a set. B sub n. It's called the Boolean lattice. And it's just the poset of subsets of the numbers from 1 up to n. So we know what this poset looks like. We said that when you draw this, you basically have drawn the hypercube, the n-dimensional cube. The bottom element of this poset is the empty set. The top element is the whole set, and we have all the different subsets in between. Okay. Why is this an Eulerian poset? Well, to show to you that this is an Eulerian poset, I have two alternatives. Either I show to you that mu of a comma b is minus 1 to the size of b minus a, or I show to you that between a and b there is an equal number of even and odd sized sets. But you'll realize that these are I mean, these are equivalent things to check by that proposition, but also they're just equally it's not that one of them is easier than the other one. Okay? So perhaps we should do it with Mobius functions just so we can practice with Mobius functions. Okay? So how do I show that the Mobius numbers between a and b alternate between 1 and -1? Well, basically, because they start at 1. Right? For example, let me show that mu of a comma b is 1. Okay? So I'm going to do it by induction on the height between a and b. Okay? Basically, I know that the Mobius numbers between a and b are just obtained by forgetting the big poset and just pretending that this is our poset. Okay? So the bottom guy is 1, then -1, -1, -1. Now, let's say that here I have k levels, or yeah, k levels. Okay? And let's assume that so far I have -1s and 1s, and let me prove that here I also have the correct thing. Now, how many guys do I have here? How many 1s do I have? 1. How many -1s do I have here? Remember, there's a difference of k between here and here. Okay? So basically, we're looking at subsets of B which contain A. And that means that I have A, and then I have k elements to play with that I can add to here. And so these are the k elements that I can add here. So I have minus k here. What about here? How many sets do I have there? Well, basically, I have to add 2 of the guys. So out of the k things, I need to add 2 of them. Then in the next level, out of the k things, I can add 3 of them, etc. And so what I get is 1 minus k plus k choose 2 minus k choose 3, until the last level that I know is k choose k minus 1. Okay? And this is the one that I don't know. So what number do I need to put here so that this adds up to 0? Exactly k choose k with the correct sign. Yeah? Because we know that 1 minus k plus k choose 2 minus k choose 3, etc. is 0. That's what we proved right there. So this is basically k choose k minus 1 to the k. And that's exactly what I needed. So this is Eulerian. Okay. That's one example. Another example. Well, we talked about this. Phase poset of a convex polytope. No matter what convex polytope it is. Okay. So this is by Euler's formula. And what I told you is that the reason is that the Euler characteristic of the ball is 1. We're thinking that a polytope is just kind of a ball that is flattened, but topologically it's a ball. And the reason Euler's formula is true is topological. It's that this number that we associate to a ball, this topological number is 1. Okay. I should say, I mean, you can prove Euler's formula combinatorially. But what's underlying, the honest reason why it's true is topological. And now we have a third example, which is Bruhat intervals, any interval in a Bruhat order. And the reason we have that is then in the homework you're going to prove this property. Okay. Now, you may have noticed that the way that I stated the homework, the way that I stated the question was, prove combinatorially that this is true. And maybe you wondered why I added the adverb combinatorially. Okay. And the reason is that, like I said, this is a property that you can think of as a combinatorial property because really it just means you kind of compute these numbers by hand and you get ones and negative ones. But in a sense, if you might be of the mindset that when something like this is true, there must be a topological reason for it. This depends whether you prefer to think about combinatorics or to think about topology. But a topologist would tell you that if something like this is true, then there must be a topological reason for this. It's not just that you kind of do something combinatorial. There must be a topological reason. And so here's a very natural question. The natural question you might ask is, are Bruhat intervals Eulerian because they fall in this category? Are Bruhat intervals phase posets of convex polytopes? Because if they were, then this would give you a new proof of this. So maybe we should try. Let's try to make a polytope that has this phase poset. Okay, E A B A B B A A B A. So let's try to make a polytope such that those are the faces. Well, this is doomed already, as you can see. How many vertices does this polytope have? So this is the empty thing. This is the empty set. This polytope would need to have 2 vertices. Well, so far, maybe that's okay. I mean, you could have a polytope with 2 vertices, but there's only one polytope with 2 vertices, which is the straight line. But here we're saying that there's 2 edges. So this guy must look like this. If it were a polytope, it would look... I mean, it's not a polytope already, but let's keep trying. Let's see what we can make. Well, here's 2 edges, okay? Now, what does this represent? Well, it represents a full dimensional thing that contains all of these guys. So this space right here. Okay? So the Bruhat interval is, it's not the phase poset of a polytope, but it is the phase poset of this. Okay? But this thing is a ball too. And I don't care that the polytope has flat edges. I care about the topology. Okay? So maybe this is too much to ask. But what you might ask is of something that is basically a subdivision of a ball. Now, if you know topology, you know you have to be careful about what you put here. Representing a ball. Representing a ball. And the correct thing to put here